All right, let's talk about the air we fly in. I mean, it's invisible, right? But think of it like this. As a pilot, you're not just flying a plane. You're sailing through an invisible ocean. And just like any sailor needs to know the sea, we pilots need to know what this atmospheric ocean is actually made of. It's step one to really mastering your flight.
Okay, so here's our flight plan for today. We're going to cover what the air is, its main ingredients, what makes the weather tick, and we'll even pop up to the ozone layer. Then we'll tie it all back to why it matters to you in the cockpit. Let's get into it.
Okay, first things first. Let's get one thing straight. The air you're flying through, it might be invisible, but it's a real physical thing. I'm talking, it has weight, it has density. Your plane literally depends on it for everything, from the lift that keeps you up to the power coming from your engine.
So, check this out, because this might blow your mind. Literally half of the entire atmosphere's weight is below 18,500 feet. Just think about that for a second. That's not just some trivia. It proves that air isn't just empty space. It's this dense fluid, and all that weight is what gives us the air pressure our instruments like the altimeter need to work, especially down low, where we spend most of our time flying. All right, so what exactly is this stuff we're flying through? Let's break down the basic, kind of constant recipe for dry air. This is the air your plane is dealing with pretty much every single time you go up. So take a look at this. The wild thing is just how consistent this recipe is. It doesn't really matter where you are in the lower atmosphere. Dry air is almost always a super stable mix. We're talking 78% nitrogen and 21% oxygen. That little 1% slice, that's just a bunch of other trace gases. But really, it's the nitrogen and oxygen that are the big dogs here. So, okay, 21% oxygen. Who cares, right? Well, you do. Your engine absolutely needs a certain amount of oxygen, we're talking about its mass, to burn fuel and make power. So what happens when the air gets thinner, like when you climb high or it's a hot day? Your engine gulps in less oxygen with every stroke, and that means less power. It's a direct hit to your performance. This is the whole idea behind density altitude, and it all starts right here.
Okay, so we've got our constant recipe, but now let's talk about the stuff that isn't constant. And honestly, this is where things get really interesting, because these are the ingredients that are responsible for pretty much all the weather you're ever going to have to deal with.
And the number one player in the variable category is, you guessed it, water vapor. Just look at that difference. In a cold, dry polar region, it might be almost nothing. But in the humid tropics, it can be up to 4% of the air's volume. That's a huge swing. And here's a fun fact that trips people up. Humid air is actually less dense than dry air. Why? Because a water molecule is lighter than the nitrogen or oxygen it's replacing. And less dense air, well, you know what that means for performance.
So this leads to a really important question for us pilots, right? Water vapor is an invisible gas. You can't see it. So how in the world does it go from being totally clear to becoming a thick cloud you definitely can't see through?
Well, the answer has this kind of fancy name, hygroscopic nuclei. But don't let the term scare you. All it means is that there are these tiny, microscopic particles floating all around us. We're talking dust, salt from the ocean, even soot. The best way to think about them, they're like tiny little seeds that a cloud needs to grow on.
So here's how it works. You've got your invisible water vapor just hanging out in the air. Then it finds one of these little nuclei, a dust particle, whatever. The water molecules start to cling to it. Then more molecules join the party, and pretty soon that little particle has grown into a visible water droplet. Now multiply that by billions and billions, and boom, you've got yourself a cloud, or mist, or fog. All the stuff we really care about when we're planning a flight. Okay, so water vapor is the king of weather down here where we fly. But there's another super important ingredient way up high. So let's climb up into the upper atmosphere for a minute and check out a very special kind of oxygen that has a massive job.
And that special ingredient is ozone. It's basically a souped-up oxygen molecule, O3, and it forms this protective layer way above us. We're talking between roughly 50 and 115,000 feet. So what does it do? Simple. It's the planet's sunscreen. It soaks up a ton of harmful UV radiation from the sun. Now, is it going to affect your VFR flight today? Probably not, but it's absolutely vital for life on Earth. And the coolest part? It's made by the very thing it protects us from. So, the sun's UV radiation comes in and zaps a regular O2 molecule, splitting it in two. Then, one of those free-floating oxygen atoms bumps into another O2 molecule, they stick together, and voila, you've got O3, ozone. It's a really simple, but kind of beautiful process, right? Okay, we've gone through nitrogen, oxygen, water vapor, even ozone. So what? How does any of this actually connect back to you, sitting in the cockpit? Let's tie it all together.
Here's the bottom line. Think of it like this. Your plane's performance relies on the constants. That steady 21% of oxygen feeding your engine. But your safety, your decision-making, that all hinges on the variables. How much water vapor is in the air? Are there enough of those little nuclei to turn it into fog? Getting a handle on this balance between what's predictable and what's not is basically the heart and soul of aviation weather.
So it really all comes back to this one idea. We are flying through a living, breathing sea of air. And knowing what that sea is actually made of, both the parts that stay the same and the parts that change, is the absolute bedrock for understanding weather and, most importantly, for flying safely.
So now we know the ingredients, but that's only half the story. Because what happens when you start changing the temperature and pressure of this airy recipe? Well, you get huge effects on your aircraft's performance. And that is exactly what we're going to dive into in the next explainer. I'll see you there.